speaker this afternoon, Nicola Marzari from EPFL and the Paul Scherrer Institute on the great acceleration in the design and discovery of novel materials. Thank you.
Okay, cool. Sorry, I think I hadn't heard you before. Can you all hear and see me well? Huh?
Yes, thanks.
Super. Okay, so my background is really material science and condensed matter physics. So I wanted to tell you a little bit of what is going there in that field. Of course, being this a talk about simulations and computational discovery, I think the key statement to make first is that in general, our science has been enabled by ICT technologies, and this is coming from the supercomputing 500 the supercomputing conference, the list of the top 500 supercomputers, slowing down a bit in the last few years, but we have been on a cycle where for many years we had doubling of capacity every 14 to 16 months, and so already this could sort of give the sense that this is a driver that doesn't exist anywhere in experimental science, and one sees the effects of this in actually the impact that computational simulations have had in, I would say, the entire scientific medical engineering literature. This is by now 7 years old, but Nature did the study of the most cited papers ever. And it's interesting that the most represented field with 12 papers on the top 100, 2 papers in the top 10 was about computational quantum mechanics, in particular using density functional theory. This is even more remarkable if you look at, say, domain-specific journals, in this case physics, and these are the journals of the American Physical Society, Physical Review Letter, Review of Modern Physics, and so on and so forth. And basically, if you were just looking, the most cited papers ever, again, we have 18 in red out of 20 papers that are all about density functional theory and computational quantum mechanics. Of course, this is not a statement of whatever intellectual depth, but is a statement of impact. And this impact, you'll see it in a moment, is now making it possible to really predict the properties of complex materials in real world situation with simulations, and from there start this process of material discovery. Now, many of you might actually not be material scientists, so I have 2 or 3 examples to show how novel materials have entered our economy, our technology, our society, for better or for worse. So I guess smartphones are an interesting example of the for better or for worse. Have they made our life better, or most likely much worse? But certainly they've been empowered by novel materials. I mean, Steve Jobs was able to get away with the keyboard that dominated the smartphone market with Blackberries because of transparent conductors, so materials that are transparent, so you can see the screen below, but they are conductors, so the device knows where you put your finger. And there are lithium-ion polymer batteries that can fill in the spaces. There are high-performance perovskite tantalates, and at the end, the cost of this object in terms of elements is really 50 euros in gold, 25 cents in tantalum, and 25 cents of everything else. So you're seeing, here €1 worth of materials, but it's how we put them together that empowers those technologies. Another good examples come from jet engines. Just running a jet engine, 1 degree hotter is on a worldwide scale an enormous decrease in costs. And so you would want to run, this combustion chamber here as hot as possible. And actually these days, it's a couple of hundreds degrees hotter than the melting temperature of this nickel superalloy blade that you see here, held by a Rolls-Royce engineer. This is the Trent XY body engine that runs on the Airbus 350. So not only that blade is a single crystal that has been grown very carefully so that it doesn't break apart while you're flying, but is covered by a thermal barrier coating that is enough to kill the temperature so that the actual blades doesn't melt during operation. And the last example of materials that are important for technology, society, economy. This is, I think, is an interesting case of society. I don't know if some of you recognize as Fritz Haber on the left, but basically this is the guy that has invented or discovered the most important material in the world, that is the iron-based catalyst that made ammonia synthesis possible in the 20s. And with ammonia, basically you make fertilizers that is what is needed, for better or for worse these days, to feed 8 billion people. And with ammonia, you also make bombs. So all the bombs of World War II were made thanks to the Fritz Haber process. So this was just a very brief cursory sort of overview of how materials affect our society, hopefully for better, sometimes for worse. And here is a list of the areas where novel materials really can promote change. Energy and environment are the two big problems for us, and from harvesting, converting solar energy in electricity, fuels, storing it, being more efficient, even say lightweight alloys to decrease the cost of transportation. All of these have a societal impact. A lot of countries, especially here in Europe, relies on high-tech, high-value industry. Here in Switzerland, we have a lot of pharma effort. This you might be very familiar, but basically, if your organic crystals converts after 1 year, at room temperature into, a new polytype that is not water soluble, you don't have anymore a drug or a pharmaceutical, but you have actually a brick that is completely useless. So in all of this, I wanted to, give a broad overview of this paradigm of, what we call materials revolution. These words come from actually a tech magazine that said that, powerful simulation techniques, increased computing power, machine learning are really enabling researchers to automate much of the discovery process, accelerating the development of new materials. And actually it was named one of the, whatever, by some random journalist, technology that could create $1 trillion markets. Now, if you want to do this, as you all know, you need to make sure that your simulations are actually good enough. That is, they are the accuracy that you need, that they capture the complexity of the real world, and they actually these days exploits ideas and tools from computer science, what we call materials informatics. So I won't spend much time in accuracy. It's a difficult problem to sort of explain in a nutshell when quantum mechanical simulations can be accurate enough and where cannot be. This is just an example of a problem that we can all understand. That is, what is the voltage of a lithium-ion battery? You want high energy density batteries. You want large voltages, and so this is the task of predicting the voltage in these materials, and is it going to be good enough? And so this is just an example on how one can develop advanced electronic structural methods in green here. To get to what I call predictive accuracy. The voltage that we predict in light green are as good as the experiments. Now, this is, in a very simple system from the point of view of the material, but often we want also to simulate complex systems or complex processes. So, these days we want to do electrocatalysis, so we want to understand what could be, a reaction rate on an electrode, maybe in the presence of an applied electrochemical potential with, solvent, ions, and electrolyte screening the reactions. This is a fun example that comes from a local project. As you know, being in Switzerland, there is a lot of effort that is given to Swiss swatches, and the industry here wants to be able to develop new colors for precious metal alloys. And rather than a trial and error, it would be great if one could calculate these colors in a simulation rather than in an experiment. And that's quite complex because it means understanding how photon excite electrons across bands, intra-bands in the material, and so what is the dielectric response and reflectivity in the optical limit. But this is just to say, these days we can do it very well, and the top is what we predict, and the bottom is a picture of the same material. But of course, if you can predict it, ultimately this is going to be faster than an experiment, so you can screen much more rapidly material space and then identify what is interesting or what is not. And a couple of examples more, sort of, if you are a physicist, this is a nice example of looking at a multi-physics problem, like the resistivity of a piece of material. This case is doped graphene, where you have electrons that interacts with vibration, with phonons at different degrees of doping as a function of temperature. And one can, get what are called the scattering amplitudes, with this getting the electron lifetimes and using those to solve, in this case, a mesoscale Boltzmann transport equation. But, the net result is that the calculation on the left are very predictive, and they didn't have any input parameter at all. It's just quantum mechanics and complex mesoscale physics. To the point that, sometimes you also discover that what is the current state of theory has been missing key pieces. This has been part of a fun project for us of studying materials with low thermal conductivity, like those thermal barrier coatings, and where we discovered that Boltzmann transport, when applied to heat, that is to phonons and phonon wave packets, basically was missing a very important term that is due to the tunneling of phonon wave packets from one phonon branch to the other. And so if you want to predict, say, thermal transport in a low thermal conductivity material like a thermoelectric, this is the graph here of thermal conductivity as a function of temperature, it's not enough to just take into account the diffusion and scattering of phonons, so that would be the Piers-Boltzmann equation with this green line. But there is an important term that is a tunneling term, that is the blue term, that already at room temperature you see dominates, and it's only red plus blue that gives you the black prediction in very good agreement with experiment. So the first two statement was, materials are important, and these days there are a lot of material properties that we can calculate from first principle without an experiment. So if you want the next natural step that has been around, these days for 20 years, is really exploring configurational or composition space in search of a materials breakthrough. And for this, I want to give you an example, and then I'll also, discuss actually the IT technology stack, because originally I was actually invited as part of a Cyprus supercomputing effort. So the last part of the talk will be more IT than science, but I'll show you how it can empower, say, projects like this. That's something that we started a few years ago to take all experimentally known inorganic materials and understand if they could be exfoliated into 2D layer, exactly as you can exfoliate a piece of graphite into graphene. Now, in 2 dimensions, there is a lot of interesting physics and chemistry. These are just a few of the Nobel Prizes, from the anomalous quantum Hall effect, from ITC superconductors to giant magnetoresistance. And of course, the example of graphene is very well known, where Gaiman Novoselov really scotch taped a piece of graphite, getting a monolayer out of this. And the idea is, can we discover the next graphene? And so what we do for a high throughput discovery project like this is that we have ingested all databases of inorganic materials. We screen those for materials that look like they could be layered, and if they look promising, we do a lot of calculation on the parent compound, on the child, basic characterization, and then physical properties. And it's not only us, many groups in the world work at this topic. But the issue, what we have put really an effort here is to build this infrastructure to really make this kind of research not only possible, but quite routine, where we want to be able to work with large databases of experimental data, of computational data, and basically calculate properties data on demand. So we would like to start from a material and say, in this case, predict what is its elastic tensor through a very complex workflows that is, by now, reliable and robust. So you don't need any expert to do it. Anyone can push the button and get the property that one wants. And, for this project, exactly, we built the workflow. Here you see a graphical representation of a single workflow that takes one material and calculates some properties. We'll discuss later this directed acyclic graphs, but basically we have ingested all these materials in our databases. So we construct automatically a standard primitive cell for that inorganic material, and we do a number of quantum mechanical density functional theory calculations to basically identify the ground state for the electrons, the magnetic ground state. Is it an insulator? Is it a metals? What is its geometry? Is it relaxed? Is the stress zero? Are there any soft mode in the phonons, in the sort of normal modes? And as I said, we want to do this in an automated fashion in, say, high throughput, robust and reliable ways. And, this is done day in and day out. It goes into our, let's say, human readable form, into our curated database, where, here exactly this is the result of a calculation. For this vanadium bromium oxide, you see, what we have calculated in terms of being exfoliable, very low binding energies, an antiferromagnet with this band structure, this phonon dispersion, these cell structures, and with all the properties that we are looking for. So in this project, we started with roughly 500,000 inorganic materials. A lot of them might be disordered, amorphous systems, have a fractional occupation and so on. So we had 180,000 stoichiometric materials, of which at the time we worked with 2 databases, 108,000 were unique, 5,600 look layered, and on those we ran roughly 500,000 quantum mechanical calculations. So this is also interesting. I mean, the CPU costs of these projects were $40,000. So that you can say it's a little or a lot depending on your perspective. But this is what we found. That is, all points are one of these 5,600 materials, and we plot these materials according to the binding energy of the layers. So this is graphite, low binding energy for one monolayer, and the structure of graphite is very strongly driven by van der Waals interactions. So you see, if you put all the materials that we have, we roughly cluster them around 3 groups. The blue groups of materials that are mostly van der Waals bound with very low binding energy, we call them easily exfoliable. And we find not only graphite or boron nitride, but transition metal dechalcogenides, black phosphorus, and so on. Then we have some green materials that might be exfoliable, a bit tougher. And then we have a lot of materials that are layered, but really a very large binding energy because, typically they are intercalated with cations and anions. So it's almost ionic, the character, and you can't break them apart easily. But, the net result is that all of a sudden we don't have, one 2D material or 20, but we have 1,000. And right now we have actually kept going on this project. So we have 2,000 exfoliable materials. And the question is what to do with this. And, there are a lot of projects that one could do. One could look for magnetic metals, magnetic insulators. Magnetism in 2D was thus shown for the first time to be possible in 2017. We find materials that are semiconducting on one spin state and insulators on the other. We find material that have, bands that are metallic, but very distant from the rest of the conduction or the valence. Those could be good as transparent conductor or as materials for plasmonics. Let me give you a few examples of work in progress that is starting to look interesting. We are looking for new superconductors, and on this material that you see can be synthesized extremely well into layers. We have a prediction right now of a transition temperature of 22 Kelvin. That would be a world record for a 2D material, and in particular is higher than liquid hydrogen. And there are a number of groups that are trying not only to make, it's very difficult high pressure synthesis, not only to make this material, but to exfoliate it. We are looking at materials for photocatalysis or membranes for separation. But one of the projects that we have completed that was more extensive was the discovery of topological materials, what for 2D are called quantum spinol insulator. I don't know if there are condensed matter physicists in the audience, but this is really systems in which you don't really need a magnetic field as in the Haldane model. Haldane Duncan won the Nobel Prize in 2016 for his idea of what is a topological insulator. Here it comes from spin-orbit coupling. And actually it's a nice story. I mean, we find this material called JACUTINGAITE that was discovered in 2008 by a Czech expedition of mineralogists in Brazil. It's in Minas Gerais, and they, found this platinum compound. They published it in the Canadian Mineralogist. We ingested this data in our databases, and we found that this material actually has an hexagonal patterns of mercury atoms, but it has a very large band gap. So this, for those of you that are expert on this, means room temperature operation. You see half a band gap, half an electron volt band gap, but with these very distinct topological bands. And this was exciting enough to get our experimental colleagues fired up. So they made these materials. We had already predicted that it was quite insensitive to oxidation, proton attack, water. So, it could be manipulated, say, at ambient conditions. And you see exactly now the comparison between theory and experiments, seeing the topological bands that we had predicted. So this was an example, basically, of discovering novel materials for applications. This is a work that is very much in progress. As I said, we keep discovering novel candidates and looking for new properties between those candidates. Another example, and then I'll finish on the science part, is looking at lithium-ion conductors. So, your typical lithium-ion batteries explode because they short circuit the anode and the cathode. The liquid electrolyte is very flammable. The batteries these days pack 1/10 of the energy density of a bomb. So there is a lot of energy there ready to go. And so, they are dangerous. These days, you can't bring batteries on an airplane besides one spare replacement. And in this, what we need to figure out is actually the diffusion characteristics of lithium ions in a solid state matrix. And that's a process that is very slow. We can't do it with brute force of first principle molecular dynamics. And so what we do is we machine learn the potential energy surface with neural network and with kernel regression methods. This is an unrelated example, actually, showing how well you can machine learn, say in this case, a ferromagnetic iron with, in this case, a kernel regression method. But once you have done that, you reproduce perfectly the potential energy surface, you can study the system at time scale and at length scale that you couldn't study with direct brute force simulation. And so we are doing this for solid state inorganic electrolytes. So basically, we look for every material that contains lithium in our inorganic database. We automatically fit either a physics-based model or a machine-learned force field, and out of that, we calculate from molecular dynamics at different temperature, the diffusion coefficients, and the activation barrier. And again, this is very much work in progress. And again, one of the nice things is that these days, this work is completely funded by industry. That just means that it's relevant enough for them to invest. Okay, let me conclude the last, I think I have probably a bit less than 10 minutes given when we started, on comments that are more related to the HPC community. And it has to do with, say, the technology stack that one has to put together to do this kind of research. And if you want, there are 4 components to this. There are quantum mechanical simulation codes. Maybe some of you are more familiar with codes like CP2K. We use a lot quantum espresso for condensed matter physics, but these are community open source codes. What we have built, and I'll briefly present, is a very sophisticated Python operating system for high throughput computational science that allows us to build this reliable automated workflows that then can be used by non-specialists. So we expose our capabilities both in the form of, say, Jupyter Lab notebooks, or more general with the model of a platform as a service, and that will be the materials cloud. So in case you're interested, this would be for the case of the operating system, automated interactive infrastructure and database, AIDA for computational science, is described in this couple of papers. Again, it's all open source, but AIDA was meant to take care of these 4 core pillars, if you want, of high throughput computational science. And in particular, we wanted to make sure that the automation, that is sending thousands of calculations every day on remote resources, and the storage of the results of those calculations and the monitoring were taking place in this directed acyclic graph that preserve the entire provenance tree of all the calculation. But basically, we wanted these 2 very boring activities to be taken care by the operating system. And as scientists, we wanted to work in this green pillar of a high-level workspace where we build our scientific workflows for simulation and for data analytics. And if anything, we push and pull data and workflows to a social ecosystem of repositories around the world. And actually, this is just coming from last Friday. For those of you that are in sort of exascale computing, this is one of the first 3 of the pre-exascale European supercomputers coming online. This is the LUMI consortium. LUMI is sitting in Finland. We had access for 12 hours to the machine on Friday night. And so these are 200,000 cores. So it's 1536 nodes of 128 cores each. And you see basically AIDA effortlessly saturates with thousands of calculation a pre-exascale machine just out of our workstation here. And so we are just doing actually a post-mortem analysis today, later after this talk, in sort of the data on this. But this is just 12 hours run. using in full, with full efficiency, 200,000 cores. Let me show you another example instead in which these capabilities now become exposed to experimental groups. So this is a laboratory at EMPA. This is the materials laboratory in Dubendorf, close to Zurich. And a laboratory there works a lot on nanoribbons, on metal surfaces or self-assembled monolayer. And they greatly benefit from very sophisticated many-body perturbation theory, GW calculation for electronic spectra, IV characteristic, STM images. And these are the, experimental PhD students and postdocs that now routinely use this, we call it AIDA lab, this Jupyter lab, say, front end that allows to expose this workflow in a user-friendly way. If you are interested in trying out things, we actually not only use open source codes all the way through, but we also distribute, say, a virtual machine with all these codes and AIDA already installed and ready to go. This is, also another example in, trying to make scientific statements. Here, we have put together a consortium of 40 scientists, 11 different codes that have now, say, common, we call it service interfaces, common workflow to run the same calculation on all these codes. So something like the dissociation of hydrogen or aluminum, the equation of state. Well, ideally, you would like to get the same results, no matter what code and what methodology you use, provided it's the same theory. And, we are almost there, but not quite. So this is, I think, an important verification step for the community. And last, let me conclude, this is how we actually deploy this platform. So this is at the Swiss Supercomputing Center. And this is the architecture of our platform, the Materials Cloud. You go there and you would find, the different sections: learn, work, discover, explore, and archive for educational materials, for online simulation services. And discover, explore, and archive are data, say, pillars where we expose raw or curated data to the community at large. So this is an example for our 2D projects. You can go, and as it is, very common these days, you can look at the, properties that have been calculated. I think what is unique with respect to what we do is that, every calculation is part of a directed acyclic graph that keeps all the provenance. So you could, download if you want the database, but you can also graphically, click on that and explore layer by layer this graph. And for every node, you see all the, elements, the inputs, the outputs. And so you can easily investigate here graphically, but also with queries if you download the database, everything about what we have done. And last, in case you're interested, we run exactly like there is an archive preprint server, these days very common. We run a public archive for computational data where everyone in the world can submit data. And these days, this is an official repository for the European Commission, for the journal, Open Horizon Europe, and Open Research Europe, and for Nature Scientific Data. So 2 minutes and I'm done. Let me actually sort of make a more general statement about science and what I call science as a digital infrastructure. For this, I use Jeff Bezos, that might not be the most pleasant person in the world, but realized that 20 years ago that Amazon was a mess, in the same way that often our research infrastructure is a mess. And because he was the boss, he said, you have to do this. And what he said they had to do is that every unit in Amazon had to stop communicating with each other in any other way than expose data and functionalities through externalizable service interfaces. So every capability in Amazon is an externalizable service interface. And we want a lot of that, certainly in computational science, where everything can be an externalizable service interface, but also in experimental science. And that's where we start to have, robotic experiments that can handshake with simulation and they can become autonomous because they can be driven by a digital technology. So this is just one example. Maybe we started 5 years ago with the community to build a universal API to interrogate all database of materials. And these days you can do this. You can decide which database to query, get the material that you want, and retrieve it. And if you want, you can also launch a calculation automatically using exactly the tools that I was telling you. Okay, I think it's good that if I finish it here. So conclusions. Materials are important for better or for worse. I don't know if we want a better economy, but certainly a better society. And the two important statement is that these days we can discover materials with a speed that mirrors IT technologies rather than, say, brick and mortar laboratories. And very beautifully, it's open science. So we can redistribute the codes, the tools, the data, the services at zero cost to the entire world. By the way, if you're interested in more about this topic, we just wrote a review on this for Nature Materials. Let me conclude by thanking all the team, especially at EPFL, but across the world, working on this. And at the end, also very much the sponsors and the funding. We have a Swiss National Center for this, that is a 12 years project. We have a H2020 Center of Excellence, and we have, in our case, the Battery 2030 Plus initiative, plus a lot of other sort of individual grants and sponsors. And with this, I thank you for your attention. Very sorry not to be there, never been in Cyprus, always wanted to be for also some personal reasons, and hope there will be a happier chance in the future.
Thank you very much. Do you have any questions from either the room or the online audience? If I could start with one while we're filling the audience up. You mentioned it a couple of times in the presentation, in particular through AIDA, the need to track provenance in these kind of systems, and that's something that's maturing very rapidly in a lot of the other fields that are increasingly using AI. What is the driver for it in material science? Is it recognition of people's effort, or is it being robust to making the right decisions as you go through the?
No, so that's an interesting point. So we started working on AIDA in 2013. So this was together with Boris Kozinski, that was a student of mine that is now a professor in Harvard. And we laid down the specification. So, sometimes you have somehow the luxury of doing things because you think are the right way forward. We just had been approved for this 12-year project. And so, we were thinking, what should we do that makes a lot of sense? High throughput simulations, so, had already sort of become very relevant, let's say, apart from the Jens Norskov pioneering effort and Gerd Seder in the early 2000s, but, in 2012, 2013, were by now part of our say, power tools. And we felt that it was very important because, a lot of the properties that we calculate come from such complex workflows that we actually keep track on how we obtain a certain result. Because it's not only a matter of running one, say, code, it's running maybe the same code a lot of times or a lot of interconnected codes. And, there is no verification of what you have done if you can't track this provenance. So it was a strategic decision that cost a lot because it's not simple to set up something that never breaks that provenance and always tracks. But we thought it was the the very important thing to do for computational science.
I think a lot of other fields will be agreeing with you now. Any other questions? Any from the audience online? In that case, I'd just like to thank you again. Thank you very much for the talk, and we'll move on to the next speaker. Thank you.
Thank you.